Okay. All right, so the recording's on. I trust everyone is doing well, and I will just talk a little bit about some ideas that Mike and Christian and I were talking about on Thursday. We were just, Christian had just given his talk at MIT, and Mike and I were kind of going over some things about the rewrite rules, like where do you place the hold in order to have in order to knock a hole in the left-hand side of the rewrite rule to be a bar. And it occurred to me that we could type the holes, which then gave me the idea that we could type the rewrite rules. So let's just remind ourselves. So here are some well-known rewrite rules. So beta reduction is well understood. The com rule for the row calculus is well understood. And the N rule for the ambient calculus is well understood. Each of them is different in some way. So beta reduction applies the actual argument, whereas the com rule for the row calculus only substitutes the code of the argument. So in beta reduction, you can have consistent interpretations that are either called by value or called by name. But in the case of the com rule, it's primarily called by name unless you explicitly have a star or a deref, in which case it's called by value at that point. So it articulates that distinction more precisely. It gives a programmer control over call by name versus call by value. And in the case of the ambient calculus, you, instead of a substitution, you get a tree rewrite. So you've got a syntax tree that's located in the ambient M, represented by the process Q, and you have the process that will go into M and deposit P. And so when they're put in parallel composition, that reduces to putting P inside M and peeling off the prefix. So hopefully those are all relatively familiar, or at least, you know, some of them are familiar to folks here on the call. Does this make sense?
Yes.
Cool. All right. So, so now let's look at some types. We have a type which will check to see whether something is an application. So it's just basically the application constructor, and then you can have virtually any term or any term in the function position and any term in the argument position. And then we also have a type that checks to see an abstraction. So this is a little bit subtle because, you know, I'm thinking about a calculus where you know something about the shape of the names. So alpha is a namespace. And then you're checking to see whether or not it's an abstraction. Here is single-threadedness. So it is not single-threadedness and not zero. So it's not zero and it's not a parallel composition of two non-zero things. And dual to that, we have a multi-threaded. So it is the parallel composition of at least two non-zero things. For the, we could have a type for the ambient calculus, which is out, and again, this is a little subtle because we're assuming that the names of our ambient calculus has some kind of structure. So yeah, out to some namespace, and then become any old process. And this one's a little bit more sophisticated. So it's a recursive type, right? So it's the greatest fixed point of phi 6. So it says it's not, it's single threaded, and if it reduces at all, it has to reduce to something that respects phi 6. So it might just sit there, it might be inert, but if it's not inert, if it does a reduction at all, then it has to reduce to something that is once again phi 6. So any questions about any of these types?
In this last one, this means that we are repeating recursion, but only as a single thread.
That's right. What we're saying is the process might reduce, right? And if it does reduce, then it has to reduce to something that is once again single threaded. So it can't spawn any threads.
And the difference between the third example is, in third example, we have only one step, right? And
That's
here
right.
we have recursion, so we can.
Yes, exactly.
Okay, cool.
Yeah. All right. So hopefully that gives some general flavor and feel for the kinds of things that we can express with the behavioral, the spatial behavioral types. Right? These are pretty powerful, I think. So now, then we can look at variants of the rules that we talked about. Oh, this should have been parametric in phi 3 and phi 4. That was a typo, sorry. So we could have a beta that's parametric in a phi 1 and a phi 2. And it says that the abstraction, the M, whatever process goes in here has to satisfy this type. It's got to be an application. And whatever process goes in here has to satisfy phi 2, which means it has to be an abstraction. And in this case, so notice that would create an interesting thing, right? So we know this will reduce, right? Because n is going to be applied to x. And since this is an application, there might be an x in the left-hand side or the right-hand side. So there might be an instance of x in the left-hand side of the function position of the argument or the value position of n, right? And we know that of m. And we know that n has got to be an abstraction. So wherever we're going to plunk something down for x, we know it's going to be an abstraction. So this is a restricted form of beta that won't allow for all beta reductions, right? But only very, very restricted ones. Does this make sense?
Yes.
Cool.
These restricted ones are like we only care about functions in the position.
Yeah. Well, no, what we're saying is M has got to be an application and N has got to be an abstraction. Right? So it's insisting that this is somehow higher order, right? It's only applying to abstractions. So we can have a COM rule, which says that, which is parametric only in a Q3, which is prime. So or single threaded. So what we're saying is we're only letting single-threaded things through on the send, and we're only going to evolve to a single-threaded thing, right? Does that make sense? The P is the single-threaded continuation. So that's a new kind of COM rule that's restricted. We can do something similar. Notice that the par types apply equally well to ambient as well as rho and pi. So we get to reuse that type Q3. And of course, Q4 is that ambient type here. Sorry. It's composite, not an ambient type. I think I renumbered them and then didn't renumber them here. It doesn't matter, it still works, it still applies. So we can insist that P is single-threaded, and we're only mixing single-threaded things into composite things. That's basically what this says. Right? We're only going to allow for the ambient M, we're only letting in single-threaded things, and we're only letting them into composite mixtures. That's what this reduction rule says. Now this one is particularly interesting, right? So P is, we insist that P is composite, but here we insist that Q is not only single-threaded, but all of its evolutions are single-threaded. So wherever Y occurs in P, and it might occur in one parend or another, but wherever it occurs, we're only shipping single-threaded processes. Now, the thing that's really interesting about this one, which is the next slide, is that notice that this particular type, this last type, depends upon the arrow type, which is this one here. It's hiding as a modality type. But the arrow type, for its definition, fundamentally depends upon the rewrite rule. So now we have a rewrite rule that depends upon the arrow type, which depends upon the rewrite rule. So you have to for these things to make sense, you have to be able to ground out with these kinds of recursions. Does that make sense?
Yes, I think.
So notice that this is defining how the arrow evolves, but it depends upon the arrow here. And where it depends upon the arrow is right here. Right here is where it depends upon the arrow. So that modality is really an arrow type in disguise. And that arrow type, as we've talked about many times before, depends upon the rewrite rule itself. So we have this recursion going on, and you have to take care that the recursion is well founded, or that it grounds out. It's very similar in some respects to the annihilation COM rule that I gave in the row calculus paper. So hopefully that makes some sense.
And when you say arrow type, I'm thinking about your explanation from the paper about left and right, where the what K is telling us.
Yeah, let me see if I have the ladle. It looks like I don't. I thought I had ladle. All right, let me open the ladle thing. So we're gonna open that, of course. Okay, so here's what I mean by an arrow type. So I've put this definition on screen several times before. So here's the arrow. Right? And basically what it says is it's all the contexts such that when you apply the context to something that's of type tau, if it evolves to some term v, that term is in tau prime. So tau, arrow tau prime. Now see, here's the rewrite, and here's the rewrite. Right. So
I see.
right. So there's a circularity, and you just have to be a little bit careful that when you define these things, that the circularity grounds out. And you can kind of check those things automatically, actually. Anyway, so that's that I think so. So this is new, to the best of my knowledge. This has not been proposed before. There are typed virtual machines, but no one has proposed, to the best of my knowledge, typed rewrite systems. Now notice that you could also type the rewrite shape itself. So you could treat the language in which you rewrite rules as its own, as its own computational system, and type that as well. So that gives yet another level of expressive power. So this gives some basic idea. Now, when you combine this with some other insights, then things start to get very interesting. So for example, Yoshida shows that her combinators give rise to a stratification of the pi calculus. So each of those combinators corresponds to, a calculus, a particular form of process. And so you could typify those processes. So for example, message is just output. So the combinator message corresponds exactly to output. The duplicator combinator, you can figure out how to duplicate things on different channels as a process. Right? So there's obviously a translation of each of the combinators into a process, and you can then turn those into types, and then use these typed rewrite rules to give a stratification of the calculus as a discipline on the rewrite system. So that's a way of recasting her results, but all sort of within one framework. Does that make sense? And people following?
Can you explain what is stratification?
Sure. If you leave out one of the combinators and you look at the fragment of the calculus that doesn't use that combinator, then you get a fragment of the pi calculus that doesn't have full expressive power.
I remember now. You already explained that. Yeah.
Yes. So she basically does an exhaustive analysis. If we take this one out and leave the other ones in, and she does that for each one because there's only a handful of them. So she can give a completely exhaustive stratification of the calculus. So we can arrive at that stratification by typing the common, which is kind of cool.
Yeah. We
can insist that the things, the variables are only from the combinators that we're allowing in, the P's and the Q's. So that's an approach that falls out of this framework. So I'm pretty excited. I think this is a very handy gadget to have stumbled upon, and it's made possible with the operational semantics and logical form.
So this means we can have. So my understanding, what you said, we can have our inside our language. We can have a language which defines our rewriting rules, and we can have language which are giving us both of these. So we can apply one COM rules in one part of the program and different COM rules in different part of the program.
Yes, that's right. So the types types arise from two different structures. So one structure is the language that you're writing the rewrites over. So, right. So in the case of phi1 and phi2, or phi1 and phi2, the language that we're writing rewrites over is the lambda calculus, right? So we can use the constraints on lambda terms, which is what the types are, to constrain beta reduction. Phi3 or phi3 and phi4 are applicable both, well, to the pi calculus, the row calculus, and the ambient calculus. And so we could utilize that for the COM rule, so all the flavors of the COM rule and the ambient calculus, in, out, and open rules. So that shows that the term language gives you enough structure to constrain the rewrite, because the rewrite is always in terms of the term language. But you could also constrain, there's another language, which is the language of the rewrite systems themselves. You know, it has the left-hand side, which is a K of something, you know, some arguments, to the right-hand side, which we know to be some term in the language. So that language of writing down rewrite rules is also something that we can apply the operational semantics and logical form to, and get types that talk about the general shape of rewrites. Does that make sense?
Yeah. And do we need access to internals of existing language if we want to have types for rewrites?
So again, this is what I was saying. It's like we have two levels of types. So these kind access the internal structure of lambda terms, right? And these kind access internal structure of lambda, pi, and pi, row, and ambient, right? It can see pars and it can see zeros. So that's the language that we're using our rewrites to express. So that's one level down, and then we can also avail ourselves of the structure that's used to express the rewrites themselves. So here are our rewrites, right? So obviously when we write down beta, we're writing it down in some format, in some language. Right? So typically these kinds of operational semantics are given some kind of SOS presentation or some constrained rewrite format. And you can run operational semantics and logical form on that as well. So not just on the term language, but on the structure of rewrites themselves. Does that make sense?
On the, I'm not completely sure what you mean by structure on structure itself.
The structure of the rewrite itself, it has a left-hand side and a right-hand side. And, there might be some side conditions, right? Or there might be some predicate that is guarding whether or not this rewrite happens. So in the case of the annihilation rule, there's a guard for whether or not the rewrite happens. And that's actually quite general, right? So the par rule which is distinct from the con rule, right? The par rule says that if P reduces on its own to P prime, then P par Q reduces on its own to P prime par Q, right? So that has a hypothesis and a consequent, as well as a left-hand side and a right-hand side. Right, so it's got a vertical structure and a horizontal structure. And that, we can run operational semantics and logical form on that as well as on the term language. Does that make sense?
Okay, yeah, I think
Cool.
it does, yeah.
Cool. All right. So that's I mean, there was another interesting point. Let's see. I don't know if I have a, let me see. I don't have a drawing program on here. Hang on a second. Let me stop sharing. I'll see if I can find a drawing program. Online drawing tool. Yeah, here we go. So, I wonder if it'll, okay, yeah. All right, so let me share again. Okie dokie. Here we are. So let's look at again at the common. So we have 4. And then this takes 3 arguments, right? So there's the y, the x, and the p. Okay, so we can really say that underneath the 4, we have the y, we have the x, and we have the p. And then over here, on an x bang, all right, so what we're saying is that underneath here we have an x and a q. And then these are both, oops. These are both underneath the par, right? And now if we were to say, um, like here, if our whole is here, right? Or here, interaction is guaranteed, right? Because we've already got it set up so that we've got the right guard, which will cause the interaction. But in order for it to be a barb, something of interest, um, we need we need to move the hole. So if the hole is here, right, that's not a good barb, because the interaction is guaranteed. Oops. So let me do a select. So let's imagine expanding the hole to the next level up. So this is Mike's observation. So if we expand it to the next level up, so we're knocking a hole here on the left-hand side of the rewrite rule, then clearly that this is a good barb, you know, hole, par, output is a good barb for input, and vice versa, right? If we have a hole here, that's not a good barb because the interaction is guaranteed to happen. So there's no testing, right, that will happen. However, if we go up one level and knock the hole here, then that is, so for par hole, that's a good barb because it will test to see whether what you put in that hole is an output that will interact. So that's a way to kind of calculate the hole. And this also works for like the in rule, right? So if we have par at the top, we have in m p, and over here we have m q. Right. So if the hole is here, that isn't a good barb because it's guaranteed to interact. But if you go up one level, right, and put the hole here, that is a good barb, right? Because it'll test to see whether or not this has the shape which will interact with the ambient. So the same thing works. And in fact, if you check it against all the major calculi, it works. So all the major interactive calculi, this idea works. So this gives us confidence that we have a good notion of barb derived from context. And then as before, let's see. We can use the barb, this notion of barb, this context-based notion of barb, to derive a notion of barb by simulation for all of the any rewrite system, whether it's lambda or pi or rho or ambient or what have you. And so now we're working on the proof that that such a notion of bisimulation is a congruence, meaning that we have a cancellative property. So any questions on that?
Yeah, I'm wondering actually. It's more I guess, much simplistic question. Can we use any of this to improve the error handling and security of the current code base?
Oh yeah, that's the whole idea. Absolutely, yes, yes. The only reason we're doing it at this level of generality is that we kind of want to solve this once and for all, right? Rolang will evolve. There will be other, blockchain smart contracting languages and other programming languages and other kinds of algebra, I don't know, algebras, and calculi that we would like to have type systems for. So this does it once and for all. So we're trying to make sure that the type systems that we generate have all the right properties. So bisimulation equivalence corresponds to logical equivalence. The bisimulation is a congruence, and then as we noted, look, we get these incredibly rich types. And look at the kind of type. This, I mean, I'm barely scratching the surface, right? So, like, you can insist, for example, that you can do a mu six phi a mu phi 6 prime that is insists on being both single threaded and live. So you get rid of this antecedent before this implication. You just make it true phi 6, so that gets rid of this much of the formula. Let's see, hang on. So if you get rid of that much of the formula, then that formula says it's both single threaded and it's always live, right? So we have a one-line formula to talk about liveness and single threadedness.
Yeah, I mean, we have an outstanding task to create or improve the error handling framework. So I was wondering if using that as a case study for this might solve two problems at the same time, which is it gives, say for a published paper or something, an actual case study. And at the same time, it moves us forward on the code base.
Sure.
Something. And I don't know like if you need like Tomislav or somebody to work with you on that, or what's the right way to concretize this to the code base.
Sure. Yeah, as I've said, we have a few theorems that we want to write down and make sure that we have the formal proofs for. And once we have those, then the code will more or less write itself, but there has to be a choice about platform. So, do we want to add this to K framework? Do we want to add this to Kiyama? But because once we've made that choice, we're sort of committed to that for some period of time. So that's going to be the next choice after we get these theorems proved. But once we've made that choice, and I'm sort of leaning on rolling our own. But once we have that choice nailed down, then generating a typed Rolang is a press of a button. There's nothing to it. So that's why I'm not particularly worried about that step, right? Because literally, you just run the algorithm on the version of Rolang that you have at your disposal, and you're done. Does that make sense?
Yeah.
Cool.
So I have another question that may not be directly related to this. I was looking at this language called Ballerina, over the weekend that has static typing and also what is called structural types. And their main thing, I guess, is they say, we're cloud native, meaning all the constructs that you need for cloud programming, which we deal with a lot in the actual development, in our current development, for example. They incorporate that into the main language itself so that you can naturally work with all of those. But the question I guess I have is the structural types versus this type rewriting and namespaces. I mean, is there any relationship among them, or structural types just a poor substitute for something more elegant, or what?
So let me go back to screen sharing. This is a structural type. This is a structural type. This is a structural type. In fact, all of these are structural types, and this is mixed. It's both structural and behavioral. So but the point is, right? So in the case that you're talking about, it's a type system for a language. We generate for any language a structural type system for that language. So this algorithm takes as input a language, a programming language, and as output produces a type system. Does that make sense?
Yeah, yeah. So I guess the question then is to say, is there a way of verifying? Because I assume the ballerina structural types are derived manually or created manually.
Correct. That's right.
They put together whatever they thought made sense.
That's exactly right. They're created manually, and then they have a burden, which is to show that you have that your type system is sound and complete.
Right, and to manage the semantic integrity and all of that. So the question is, can this is another kind of a case study type of thing. Can we apply this on top of ballerina and say, well, how should they be modifying their structural types based on this? Like, let this generate and then say, here is the difference between what this generates versus what they came up with on their own.
Yes, exactly. That can be done. But what I want to concentrate on first are low-hanging fruit. So let's do lambda, let's do pi and rho and ambient, and then that will be proof that the thing works. And then from there we can move to a more complicated language, because those are all very, very tiny languages, right? Then we can move to a slightly more complicated language, which is Rolang. And then, from at that point, we have enough experience that we know that we've done we've done the thing. And there's not a lot of bang for buck in the language that you're talking about, because it's a very, very niche language, right? A more interesting thing to chew off would be JavaScript, right? Because there are many JavaScripts, and they each have their own. There are many types of JavaScripts, and each type system was generated by hand. So here we're saying, well, just give us the rewrite system for JavaScript, give us the semantics for JavaScript, and we'll generate the type system for you. So all of the work that Google and Microsoft and Facebook did to spend on their versions of type JavaScript will be completely obviated, because their types don't even have structural types. They don't have behavioral types. They just have the standard memory guards. Does this data have this shape, and is the function expecting data of that shape? That's all it's got, right? So, but we can do considerably better than that. and so the types that we'll generate for JavaScript will say a lot more about JavaScript programs, and that's kind of important because JavaScript programs are really gnarly. They can let you do really, really evil, ugly things. So having a type system to constrain it would be a great thing. So you see what I'm saying?
Yeah, I mean, that makes a lot of sense. So the next or another question is, how would you marry? So you have the type systems, but the use case for that really actually is some kind of functional requirements. And to be able to say, how do I marry this set of functional requirements to the type systems needed in a language? Specifically, I'm thinking of, let's say, one of the main applications of JavaScript is a browser. So we should be able to say, okay, this is what the functional requirements of a browser are, and then derive from it all the stuff that's needed, and link the two. Is there a link, or is that kind of future work, or that separate domain of?
I'm sorry. Can you repeat your question? I was distracted for a moment.
I'm saying basically, if we say we have a browser and here are the functional requirements of a browser, meaning if we want to build a browser, because we were talking the other day about building a browser in Golang. So how do you marry the requirements of something that needs to be built back down to this types and the language? I mean, the language and types, you're going from the bottom up, but I'm saying, is there a way to come from top down also and then create a framework that because functions or functional description of something also is types at some level. So basically we're describing types.
Notice that these types here make no, there's no program that they're associated with, right? They're completely independent of a program. So, and this is because, you know, I fundamentally believe that one of the best ways to capture requirements is to do a type-based analysis of the design. So you write down the functional requirements and other requirements as types. And that gives you a set of constraints which you can check your implementation against. So this is the whole, I mean, part of the whole impetus of this work is to be able to provide people with those kinds of tools, right? So, for example, it would have been perfectly reasonable for the people who were writing the Solidity contract to first write down their requirements for the DAO contract at the level of types, right? So they could have said, well, you know, when it comes to the general shape of servicing incoming requests versus updating state, that has to be sequential. So you could write that down at the type level and without saying much about the implementation. And, you know, I've given examples of this in papers dating back 4 years. So yeah, you can do this absolutely. If you go look at the namespace logic paper, which I published in 15 years ago, I do exactly this for XML. So I show what the structural requirements are for an implementation to be able to support XML semantics. Likewise, I give an analysis of a firewall. I say, what does a firewall look like at the level of types, and then you can check that your program implements this notion of firewall. Does that make sense?
Yeah. Yeah.
Cool. And these are great questions. I really appreciate them. Any other questions or comments from?
May I ask more more specific question. What do you expect that we need to build in the current code for as an input to generate the types?
So what we'll have to provide is an executable spec for rolling. So we'll have to give the, so there are three things that define an executable spec, right? So there's the grammar that generates all the terms in the language. There is a structural equivalence. So in the case of row calculus, we know what that grammar is, right? It's a one-line grammar. And then there's some equations, for example, that par gives you a commutative monoid with respect to 0. So 0 is the identity for the par monoid. And that turns out to be the only equation apart from alpha equivalence. And then you have an operational semantics, and the operational semantics is given by the common. So if you have those three things for any language, right, and that's what you have to have in order to say that a language is well defined. So if you have those three things, then we can generate the type system for you. Typically you want to be able to say how you collect the types, but for now we're making them very, very set-like. So essentially we're filling in that argument by default with sets. Does that make sense?
Yeah. So I'm thinking that now we have BNFC to specify the grammar, and we have a reducer which implements
Right.
all of these rewrite rules. So we need additional specification.
No, it's in the normalizer. The equations are in the normalizer.
I see. And the grammar, do we need some additional stuff to?
No, the grammar plus the normalizer plus the reducer. That's what you have to give.
Oh, okay. So this means that only that logic we now have inside the reducer, we somehow need to specify this in some way. So
yeah. So this is what I'm saying. Notice that those are sprinkled over very disparate systems, right? So BNFC is different from. It's written even the grammar is written in a different language than the reducer is, as an example. So you have to put all of that information in a format that our algorithm can eat it, right? So we'll specify what that format is. Like right now, it's kind of sprinkled all through our code, but instead we're going to say no. If you're going to give us that information, it has to be shaped in this following way.
So I'm thinking. Do you think it's a better way to generate this new format from existing code that we have so far, or existing specification, or we should create another format and then generate BNFC and other code that we need?
So what you're asking about is so you're asking about tying the two systems together. Now notice that as long as the system that you give is isomorphic to the implementation, right? So the operational semantics is isomorphic to the implementation. Then when you generate the types, you can throw away the format that you gave it, right? And just move that over to the language implementation. Now, hang on a second. So hopefully, but of course, even though the types are generated, type checking is still something that you'll want to do. But again, that's done at a different phase from implementation. from like the running the reducer, for example, or running the normalizer. You do the type checking before you run the normalizer or the reducer. Well, you might want to run the normalizer before that, but that's a implementation detail. So the main point is that the type checking is all done in an earlier phase than reduction, and so as long as you know that the operational semantics that you gave to the operational semantics and logical form algorithm is isomorphic to your implementation, then the type system so generated will be perfectly fine. You can use it to decorate your programs and then check that your programs match your types.
So you are saying this is isomorphic is between implementation into reducer and the code generated by for this type system.
Yeah,
I'm thinking we need to keep this in sync to so that this is really isomorphic.
Yes,
so,
I agree. Yeah, that's correct. That's correct. So in general, there's a little bit of a gap there. So for some period of time, what we can do is kind of like what we did with BNFC, where we generate the typing, and then we by hand integrate the generated code into you see what I'm saying? And then and the reason we might go that route, we've only got 3 minutes left, but the reason we might go that route is because a system which is going to generate the reducer from the information that we input is currently not going to be as efficient as a handwritten reducer, right? So the generated thing will be slower and not as efficient with its use of memory and things like that. Now, over time, we can get it to be better and better, but this is why I think we might want to roll our own to have that kind of control.
Yeah, this makes sense. Yeah.
Cool. Cool. Awesome. All right. So I appreciate your time. Thanks for all the engagement and the questions. It's really fun to be able to present cool new ideas when they just pop out like this. We can, I'll see folks in the Dev Stand-Up.
All right.
Thanks for presenting this. Thanks.
Thank you. Ciao,
Thank
ciao.
you.
Bye-bye. Bye-bye.